my feeling is I am personally a believer in determinism, not least because I think stochasticity is, in practice, noise is very important. It's important in weather and climate models. It's important in the brain. So at a kind of practical level, noise is important. But at a fundamental level, if you're really going back to absolute fundamentals, I think noise and stochasticity make no sense whatsoever. And I think ultimately the world has to be deterministic because I can't see anything else making any sense. But the one problem is with this, I think, the moral responsibility problem. If I believed that the Big Bang was somehow a preferred state and not just one of many equally ontologically equal states on the attractor, then I would actually have trouble with determinism because of this problem of moral responsibility. But I think that treating the attractor geometry as the fundamental issue somewhat diffuses that argument because one can no longer appeal to the Big Bang as somehow it was special and preferred over all the other states. I need to develop this argument a bit more. I mean, I kind of raised it towards the end of the book. It is a bit speculative, but the more I think about it, the more I feel it's potentially a very deep issue that I'd like to kind of explore a bit more.
So you're a believer in determinism, and then what we refer to as noise and stochasticity are just a combination of the sensitivity of systems to initial conditions, which we can describe mathematically, but it's a combination of this and then our epistemic stance toward them, and that we just don't know enough about them. So we can't get enough information about the initial conditions of a sufficiently complex system, and that results in what we perceive as stochasticity.
Yes, that's exactly right, and the fact that, as I say, we can generate. We can generate stochasticity or effective stochasticity very cheaply. And in fact, we can generate, as I was saying, you can generate it in a computer by turning the voltage down across transistors. So you can generate it at negative energy. So it's a resource that doesn't cost anything. And in fact, not only does it not cost anything, you will actually get back some of the energy that you thought you'd utilize to do more, perhaps useful things. So at a practical level, we should be embracing noise and stochasticity. But at a fundamental level, I don't think it makes any sense. And I don't think it makes any sense for the following reason, that if you gave me a series of numbers, and it doesn't matter how long the series of numbers is, that you say has been generated stochastically by a stochastic system or something, I will tell you how to get exactly those same numbers in a completely deterministic algorithm. So, you can give me as many numbers as you like. There's no way that you can categorically assert that is the result of a stochastic scheme and not a deterministic scheme. So, as I say, I think it's a sort of an obscure, it's something that just obscures things at a fundamental level. That's why I just can't, it's like in quantum mechanics. We can treat the collapse of the wave function, through the Copenhagen interpretation by some kind of random process, which kind of randomly takes you to one of the eigenvectors of your measurement operator. That's the standard recipe that people learn when they learn quantum mechanics, and it works fine. I mean, works absolutely fine. It produces all the answers and so on, but it makes no sense at a deep fundamental level, and that's the kind of key behind all of this, to uncover what is the underlying deterministic structure that has the appearance of noise when we formulate things in the Copenhagen way in quantum mechanics.
Well, I'd like to shift gears because there is one topic that I wanted to make sure that I covered today with the first meteorologist on the podcast. And so we've spoken a lot about weather prediction and forecasts in the relative short term, the sorts of forecasts that someone might make at the weather station. But how does everything we discussed about chaos and uncertainty relate to long scale climate change, which is a very charged and very important topic?
Yeah. Okay. I mean, the first point to make is that climate change is a different type of prediction problem to to a sort of 2 or 3 day or something 5-day weather forecast. And a kind of an analogy I sometimes use, and I think it's not too bad an analogy actually, is to let's imagine, I don't know, for the sake of argument, it's December the 21st, so that's the winter solstice, and let's say we're in London or something, and you ask me what the weather's going to be like in a couple of days, and I can look at the weather app and give you a rough idea. You might ask me what the weather's going to be like a month from now, and I would be probably very uncertain, probably unwilling to give you any very definite forecast. But if you ask me what the weather's going to be like six months from now, I will say, well, it's almost certainly going to be warmer than it is today, because in 6 months' time, it'll be the summer solstice. And every day after the 21st of December, the sun gets a little bit higher in the sky, and it warms, the air a bit more. And, that's now, of course, we get periods when maybe in February we'll get a cold snap and the temperatures will kind of push back again. But by and large, you can say over 6 months, be pretty damn sure it's getting warmer. And there kind of, it's not, I mean, chaos is still happening, but you've got this big external factor, which is the sun, and the fact the sun is getting higher in the sky every day. And this is the sort of external forcing that changes the climate through the year, the annual cycle, in a relatively deterministic way. And I say relatively, I mean, obviously in certainly British summers, we can get some pretty damn cool days when the weather doesn't behave. But by and large, on average, in a statistical way, it would be there's no doubt that summers are warmer than winters. I guess in parts of the United States that would be even more clear. So climate change is sort of a bit like that. It's a bit like the sun getting higher every day, but it's that the carbon dioxide concentration in the atmosphere is getting a little bit larger every day due to our emissions of carbon dioxide. Now, the difference with the sun, the annual cycle, is that this effect is not is kind of smaller on the day-to-day change in the altitude of the sun compared to the amounts of extra CO2. The sun effect is much larger. So we're looking at a kind of relatively small effect, but it's accumulating. Day on day, it's accumulating. Year on year, it's accumulating. Decade on decade, it's accumulating. So we can certainly talk about the statistics of weather, which is basically what climate is, changing in a kind of systematic way as a result of our emissions of carbon dioxide. So people that say, oh, well, because you can't trust a weather forecast more than, a week or two in the future, we can't possibly trust a climate change forecast a century into the future. They're just misunderstanding the nature of the prediction problem. And the prediction problem is much more like, trying to estimate the effect of the sun going up a little bit every day in terms of the statistics of weather between December to February and June to August or something. So that's the first point. But having said that, there are uncertainties about climate change, and the basic physics of climate change is actually not uncertain. So the fact that carbon dioxide is a greenhouse gas and that's warming the planet is kind of pretty It's 19th century physics. It was well understood then. It's well understood now. So that is not an issue. The issue around climate change is that there are various feedbacks which amplify. Now, you see, I said in the book, and actually one or two reviews from very climate sensitive people kind of criticized me for this, but I said in the book that if carbon dioxide was the only thing we needed to worry about, a doubling of carbon dioxide would only warm the planet by a degree or so, and that would take. I mean, we won't have doubled carbon dioxide from its pre-industrial values till I don't know, actually, certainly to the end, by the end of this, probably into the next century, I should think. And would we bother with one? I mean, I personally, I don't think climate change would be that much of a big deal. Now, some people argue with me about this, but I don't think, if we said, well, we're going to warm by 1 degree over the next 100 and something years, I don't think that would be. It wouldn't be the urgent concern it is. So what makes it an urgent concern is that there are other things which amplify the signal, and a kind of a relatively simple example is water vapor. So water vapor, gaseous form of water, is a greenhouse gas, and as you warm the air, the air can hold more. I'm speaking slightly loosely now, but the air can hold more water vapor. So it becomes more humid on average, and that kind of amplifies the effect of our CO2 emissions. Another quite well-known example is the effect of melting of ice, for example, over the Arctic, because the ice reflects sunlight back to space. If you start melting it, the sunlight gets absorbed by the darker water below, and that warms up the ocean. But as I say in the book, the single biggest uncertainty in climate change, and really the one that is going to make the difference between it being a kind of existential threat for humans and just being a kind of an inconvenience, I mean, a big inconvenience, but not an existential inconvenience, is what happens to clouds, so the liquid form of water, or liquid or ice. And that can go either way. Depending on the altitude of the clouds, whether they're increasing at low levels or increasing at high levels, their effect can be to damp climate change or to amplify climate change. Now, most of the models, unfortunately, suggest that clouds will amplify the climate change, so making it worse. And that really is what, for me, is the thing which I think, causes us to say we've got to try and solve this problem, because if it's the amplifier and it takes us up to levels of warming that are 3 degrees or more above pre-industrial, then we're looking at levels of climate change which will be awful for large parts of humanity. Maybe not so much for me in the UK, but people in the Middle East and parts of Africa, South America, Central America, Central Asia, could be unbelievably hellish. I mean, it could be actually levels where the human body can't actually survive anymore. So it all becomes a matter of judgment. Is the level of risk high enough to warrant taking action? I personally think it is, but I do in the book try to make the point that there are two separate issues. One is the issue of what does the science say, and I think we have to be, honest and say there are still big uncertainties about the science, and in particular the role of the water cycle and the clouds and stuff like that. We have a poor understanding of that aspect of climate change, but all the models suggest, and the models are plausibly correct. When I say all the models, most of the models suggest, and they're plausibly correct, that clouds will amplify the climate change signal, and that's what's a matter of concern. I'd personally like to see a lot more, research done on this problem, and I think it's the sort of problem that would be best tackled by an international center, something like a CERN for climate change. I've sort of argued for this for many years, actually. Climate change is such a kind of globally important problem. We ought to be tackling it at a much more global level. But, at the end of the day, because you can take the science output, you can take the output from the models, but at the end of the day, you have to make a judgment. And when I say you have to, I mean individuals maybe, and certainly politicians have to make a judgment. Is the risk of something which is clearly going to be disastrous for humanity, is that risk high enough that it's worth, changing our economy to a zero carbon economy and so on and so forth? And of course, that question is not a pure scientific question. It involves value judgments. It involves questions about how difficult it is to wean us off fossil fuels, and what are the costs, what are the benefits, and so on. I kind of feel this is where actually although I said this is not at a science level, this is not the same as weather forecasting, but there is a good parallel. We talked about ensembles in weather forecasting. So, for example, you want to go on a hike, I don't know, in the afternoon, let's say, and you look up is it going to rain or not? And let's say it says there's a 20% chance it's going to rain. So the question is, do you pack your waterproof gear? Okay, so if you don't pack your waterproof gear, then there's clearly a risk that it will rain, and you're wearing a t-shirt and shorts or something. You'll get completely soaked. It'll be extremely uncomfortable. You might start to feel cold because you're wet. On the other hand, to pack your waterproof gear, you've got to stick them in a backpack, and it's weighing something, and it's a bit inconvenient, and and there's only a 20% chance anyway. So what do you do? Well, it's not a science question. Deciding whether you're going to bring your waterproof gear or not is not a science question. The science question is, what is the probability of rain? 20%. You have to make your value judgments about how much the discomfort of being soaked compares with the inconvenience of carrying heavy waterproofs in a backpack or something. It's similar for climate change, but it's much more serious. We have probabilities of reaching 3 degrees, 4 degrees, and so on. But the question of whether it's worth doing something about it involves value judgments. And in the book, I try to separate out these two issues. I have separate chapters, one on the science of climate change and one on the sort of factors that you have to think about when you're making this judgment about, are the probabilities high enough? And I deliberately chose them as having separate chapters to make the point that one is about science and one, in a sense, is not about science. It's about how to use science, but putting in value judgments. And I personally feel it is worth, in fact, I think it's almost a no-brainer that we should take action to avoid these risks. But I say that I'm saying that partly as a scientist, but partly just as a human being living on the planet. I mean, not with any particular expertise, but just knowing a bit about the probabilities and the costs and the damages and so on. But I feel when I go onto YouTube and I don't know, see people focusing on minutiae of the science, I kind of feel they're missing the big picture. And the big picture is there is demonstrably a risk of, very serious levels of climate change. I mean, we don't know for certain, but there's demonstrably a risk. I mean, there's no question whatsoever. There is a risk. But the question is that risk high enough that it's worth to take action? And I feel by kind of going into the minutiae of the uncertainties in science, we're kind of missing that big picture. Because just think about it in life. When do you ever make decisions in life knowing absolutely what the future is going to be like? You never do. You always have to make decisions where things are uncertain, and climate change is no different to that. It's not the case that with complete certainty we're heading into an existential catastrophe. And similarly, it's not the case that we are unquestionably, the climate change is a kind of a minor kind of perturbation of no significance. We have to deal with the problem probabilistically, but out of those probabilities make informed decisions about what is the best to make, what is the best decision to make. So
everything you've said sounds extremely well reasoned to me. And just to sum up, the disastrousness of climate change, as you see it, probably hinges on the behavior of clouds, which we don't understand well enough, but most models suggest the outcome will not be favorable. And your appraisal of the evidence is that the risk is high enough to motivate action. So then the last thing that I want to ask before we finish is just what action would it motivate? What are the main options? Is geoengineering one of them? Just cutting carbon emissions? What could actually prevent the potential disastrous outcomes of most models?
Well, the problem with geoengineering, so there is one potential route to geoengineering, which is you spray the stratosphere with aerosols, which would reflect the sunlight back to space. But the problem with that is, again, because of the complexities of climate, we're not completely sure that might not do more harm than good. We might end up shutting off the monsoon circulations, which would, end up with billions of people not having enough food, or we might end up, shutting off the moisture supply to the rainforests, which would then lead them to be a major source of carbon. So we end up going backwards. So I'm not at all a fan of geoengineering, although I think it's something we have to do research on to understand it better. But I don't think that's a solution. I personally feel, again, this is my own view, that we need to embrace all of the technologies that could help us. I'm worried about putting too much into renewable energy because of the problem of intermittency of wind and cloud. For example, in the UK, we're certainly putting a lot of there's a lot of development of wind turbines in the North Sea, and there are plans for more out in the Atlantic and so on. And we're certainly building up a lot of solar capability. But we get periods of weeks or longer where the wind hardly blows at all. You get these big anticyclones forming over the UK. Again, one of the uncertainties about climate change is we don't know actually whether these might become more frequent in the future, in 50 years from now, which would, and given that we're moving to an economy where more and more of the energy we need for, transport, for heating, for industry and so on, is coming from electricity, then I think being overly dependent on wind and solar, I think, is a risky solution. So I'm personally somebody who's in favor of, for example, nuclear, new generation nuclear. I'm particularly keen on the so-called thorium reactors, which there's a lot of interest. In fact, China is building a prototype, which have a lot of advantages. But, I think we need, and I personally would like to see, more development of carbon capture. I think I don't particularly see why we should stop burning gas and so on if we can capture the carbon in a reasonably economic way. So some of these things like carbon capture and nuclear are not well considered by some environmentalists. But my own feeling is that this is such an important and urgent problem that we shouldn't let ideology get too much in the way, and we should embrace all of the technologies that we can to solve this problem. And if carbon capture and nuclear are part of that, then I think we should invest in that too.